Previously, we discussed frequency flat fading. Now, what do we mean by frequency flat fading is this. If this is the time axis, this is the frequency axis, and this is the amplitude. So within the range, within the band of frequencies, nu1 and nu2, the amplitude of the signal will remain unchanged across this frequency range. Although it will vary with time, but across the frequency it will remain unchanged. That means the amplitude response is flat across the frequency. As a result, we get frequency flat fading. Now, in order to study frequency flat fading, we can send a single tone in this range of frequencies. So let us say S tilde of t is equal to 1. Now from the previous expressions, we have the expression for RT, that is the received signal at the receiver, the R tilde of t, the complex envelope of the received signal, and then if we consider S tilde of t is equal to 1, we will have R tilde of t is equal to summation n is equal to 1 to n Cn e raised to power j phi n t, which previously we studied that this is equal to the channel impulse response, which is basically an impulse in case of frequency flat fading. So this can be expanded to this form by opening this e raised to power j phi n t. So we will get cos phi n t plus j sin phi n t. So then we can consider this term, the first term, as the hi of t and the second term as hq of t. So furthermore, we have also considered that we know that phi n of t is a function of more components apart from this fc tau of n, and we know that even a small change in tau n of order of 1 nanosecond can give rise to a 2 pi degree of phase shift. So it is reasonable to assume that phi n of t is uniformly distributed between 0 to 2 pi. This assumption is very valid and it is also well validated. So to proceed in our analysis, our first assumption is that phi n of t is uniformly distributed in 0 to 2 pi. So also apart from this phi n t, we also have Cn, which is kind of random in nature because Cn represents the scaling factor of the amplitude of the signal across each of the multipath. So Cn are basically random, but the simplest assumption is that Cn can be treated equal to 1. This is the most simplest scenario where Cn is equal to 1. So when Cn is equal to 1, these are uniformly distributed. And also we have a sum of n is equal to 1 to n on top of the uniform distributed. So since this n would be greater than, we are taking the assumption that this n is greater than 6. So when this n is greater than 6, we can invoke the central limit theorem on this hi of t and hq of t. So as a result of the CLT, we can assume that hi of t and hq of t, they are Gaussian distributed. And the PDF of Gaussian distributed is given by p of x is equal to 1 by under root of 2 pi b e raised to power minus x square upon 2b, where b is equal to omega p upon 2, where omega p is the total received signal power. So till now what we understood is, if we consider the signal, single tone signal, that is S tilde of t is equal to 1, this h of t, which is the channel coefficient, of flat fading, can be represented in the real part and in the imaginary part, where the real part, look at this example, this h of t can be represented in the real part and the imaginary part, where the real part is Gaussian distributed and the imaginary part is also Gaussian distributed. So h of t is basically a complex Gaussian random variable. Because of this complex, we have real and imaginary, so we have this complex Gaussian randomly distributed. So with this, we have some knowledge on the channel coefficient of flat fading h of t. Now let's see, in communication, if we send a signal x, what we receive at the receiver is x plus w. This is ideally when we consider that there is no channel, and w is the noise, which is additive due to the addition, and void Gaussian. Now if we consider the channel, that is h of t, we can write it as y is equal to h x plus w. So what we have of, because of h, is, if earlier we have the signal, the signal that is transmitted is represented by this, then as a result of AWG and noise, we will have some signal variations like this. Then on top of that, due to this h, we are unsure about the levels of the envelope of the signal. It could be here, it could be here, or it could be here. So let's say because of this wireless channel, we got this one. So it is still very difficult to realize what is the signal envelope of the received signal y. So h is getting multiplied, will lead to a level getting shifted to any value, and we do not know what is that level. So our job is to design a receiver that should be such that we have to reconstruct this signal back. So the job of the receiver is to reconstruct this signal back, and then we have to understand for that we have to understand this h, the behavior of h. And from our current discussion, we know that this h is complex Gaussian distributed, and accordingly we will design the receiver. So based on this, we have r of t is equal to real part of h of t into e raised to power j 2 pi fct, where this can be represented in the imaginary hi cos 2 pi fct plus hq sin 2 pi fct. And if we take the received signal power, so we can write this as mean of real part plus mean of imaginary part, which is equal to summation n is equal to 1 to n cn square. Now the envelope of ht, because we wanted to know the level of the signal, so we are interested in the envelope of ht. So it is denoted by alpha of t. So alpha of t is equal to mod of h of t, and h of t is hi of t plus jh q of t, where this is Gaussian distributed, this is also Gaussian distributed, and alpha t is Rayleigh distributed, provided the expected value of HIT is equal to expected value of HQ of t is equal to 0. So this why this envelope is important. So this envelope, the interest in envelope lies because it gives an indication of the signal power, and in our case it is Rayleigh distributed, and Rayleigh distributed is a simplistic distribution. It helps us to analyze the communication system, and it is mostly used in most of the analysis, and the expressions are really easy. So as a result, we also get very good mathematical expressions that are easily tractable. So the PDF of the Rayleigh distribution is given by x upon b naught e raised to power minus x square upon 2b naught, where x is greater than 0, and for x less than 0 it is 0 because envelope can only take positive values, where b naught is equal to omega p by 2. And also we are also interested in the square of envelope. So the square of envelope, that is the power, is exponentially distributed when the envelope is Rayleigh distributed. So the assumption is this. So what we have studied till now is that we rely on two assumptions. First, when the phi n is uniformly distributed between 0 and 2 pi, and the second assumption that n is very large, so that we can invoke channel limit theorem. So as a result, we can add up all the distributions, and in the end we get Gaussian distribution. So as a result of which we have this Rayleigh distributed, the envelope is Rayleigh distributed, and the power is exponentially distributed.